3D human pose and shape estimation has reached a high level of maturity on dry land. Parametric models like SMPL allow us to map human biomechanics from monocular video by assuming clear line of sight and linear light travel. But when you apply those same terrestrial models to a submerged subject, the tracking instantly fails, causing the 3D mesh to glitch, limbs contort, and the underlying skeletal structure collapses. This occurs because the aquatic environment degrades the visual signal. Light attenuates rapidly, splashing water creates physical occlusions, and the water-air interface refracts light before it reaches the lens. Calculating these environmental variables directly is not feasible for standard in-the-wild video. To perform accurate ray tracing, a system would need the exact camera intrinsics, the water's refractive index, and the precise geometry of every ripple on the surface. Because the surface geometry and optical parameters are typically unknown, terrestrial assumptions do not apply. Recovering human motion here requires discarding direct physics simulations in favor of a different architectural approach. That approach is the Underwater Human Pose Estimation Pipeline, or UW-VAE, a framework designed to bypass explicit optical physics calculations. The architecture relies on two overarching modules. First, a pre-process stage extracts an initial baseline pose from the video. Second, an optimization stage refines that data to construct the final 3D model. The core engine of this framework is a domain-specific variational autoencoder, or VAE. Instead of modeling how water bends light, the system uses this VAE to inject biomechanical priors, correcting geometry distorted by the environment. By treating environmental distortions as noise to be filtered out, the architecture recovers 3D human structure from a distorted 2D input without ever modeling the physics of the water. To understand the mechanics, we begin with Stage 1, pre-processing. The objective is to generate an initial 3D pose estimate from a single frame of video. This image shows the front end of that stack. A YOLO detector crops the swimmer, passing it to HRNet. HRNet maintains high-resolution feature maps, localizing 2D keypoints even through dynamic blur and water distortion. Those 2D pixel coordinates are then fed into the final step of the pre-processing phase, a part attention regressor, or PARE, which predicts the initial 3D pose and shape parameters. PARE is selected because it utilizes a dynamic attention mechanism to evaluate the reliability of different body parts. If a swimmer's arm is obscured by a wave, the network reduces the mathematical weight of that specific limb. By ignoring occlusions, PARE provides a robust initial 3D guess that survives the chaos of surface splash. However, this estimate is still vulnerable to the geometric distortions caused by refraction. While PARE can handle splashes, the initial 3D pose estimate remains warped because the light itself has been meant. Terrestrial pose estimation assumes light travels in a perfectly straight line from the subject to the lens. But underwater, light bends the moment it strikes the water-air interface. When the computer applies straight-line mathematical assumptions to these bent rays, it calculates false depths and angles. This forces the digital skeleton into anatomically impossible contortions. Because monocular video provides no data on the shifting surface geometry of the water, calculating the precise path of every light ray is not feasible. The system therefore requires a Stage 2 mechanism to override these resulting geometric errors. The solution to the refraction problem is the pre-trained Underwater Variational Autoencoder, or UW-VAE. The encoder, in green, maps warped pose parameters from pre-processing into a condensed 32-dimensional latent space. Trained exclusively on valid swimming kinematics, this space acts as a filter. The decoder then expands the data, reconstructing the pose based on biomechanical rules. Every set of parameters reconstructed by this VAE is constrained by the limits of the training data, mapping the estimate back into a valid human swimming posture. The UW-VAE acts as the system's implicit physical constraint, a data-driven method for ensuring anatomical plausibility when direct optical modeling is unavailable. With the VAE established, Stage 2 enters an iterative optimization loop. The VAE's internal weights are frozen, and the system executes a gradient descent to finalize the pose. This loop relies on an objective function with 3 constraints. Prior loss pulls the distorted mesh toward a biomechanically valid state. Reprojection loss aligns projected 3D joints with 2D keypoints. Smoothness loss penalizes erratic jitter by measuring joint acceleration across adjacent frames. Without the VAE PARE acting as an anchor, the reprojection loss would dominate. The system would twist the limbs until they matched the refracted pixels on screen, resulting in broken joints. The final pose is solved through the tension between these constraints, matching the observed 2D pixels, while remaining within the 3D anatomical rules enforced by the VAE. Designing this architecture revealed a major problem in aquatic vision: the lack of 3D annotated training data. Deploying a calibrated, multi-camera motion capture system underwater is difficult and prohibitively expensive. To solve this bottleneck, researchers utilized the generative power of the UW-VAE itself. This image shows the solution. By randomly sampling values from the VAE's latent space, the module can output thousands of unique, anatomically correct 3D swimming poses at scale. As seen here, these generated poses are bound to digital meshes and rendered in 3D engines with simulated water physics, varied lighting, and diverse camera angles. The UW-VAE not only optimizes individual frames, but actively generates the training data required to build and refine the entire system. This synthetic dataset is then used to fine-tune the HRNet 2D detector at the start of the pipeline, adapting it specifically to aquatic lighting and blur. This grid displays the results on real-world footage. The architecture produces accurate 3D reconstructions across multiple stroke types, ignoring splash and successfully correcting for light refraction. The UW-PE architecture demonstrates that when explicit physical modeling is obstructed by environmental variables, domain-specific generative priors provide a viable alternative for reconstructing 3D motion.